Hello everyone, welcome to a fresh new lecture on the topic Fourier Analysis for the course on Signal Processing Algorithms and Architectures. This is Dr. Anirban Dasgupta and let's get started. So, as I said in the previous lecture that these are the components of frequency domain analysis, like we have Fourier analysis, frequency estimation, PSD estimation, Z transform and coherence analysis. So, here we will start with Fourier analysis. So, Fourier analysis, just an intro which I gave in the previous video, is used to represent the signal as a sum of sinusoids like sines and cosines, which are with different frequencies, amplitudes and phases. So, the goal is to understand the frequency content of the signal. So, for discrete time signals, because here we are mainly focusing on discrete time signals, so there are two common Fourier analysis. One is the discrete time Fourier series or DTFS and the discrete time Fourier transform DTFT. So, what is the discrete time Fourier series? So, this decomposes a periodic discrete time signal into sum of sinusoids with discrete frequencies. So, this is the formula. So, here this is the synthesis equation. Here we see that this x of n, which is a periodic signal having period n, is sum of these n components. And how to get this value Ck? So, Ck is obtained by this formula 1 by n summation 0 to n minus 1 x n e power j 2 pi k n by capital N. Now, this complex exponential was introduced earlier in the time domain topic. So, if you see this signal, this is a cosine wave and this cosine wave is a discrete cosine wave which is periodic. Although you are seeing a part of this cosine wave, this is varying from negative infinity to infinity. So, if I decompose into the Fourier series, we will see that this is having only one component, and this component, of course, there is a component at 10 and minus 10, because this is a 10 hertz signal and this is mapped back to the original continuous domain spectra, because here this is frequency in hertz, just to demonstrate that how can I represent this cosine wave of 10 hertz with just one value. Now, one takeaway in this graph is that, so in time domain you have to use infinite number of points, or minimum you have to use points which contributes to one period, but in the frequency domain you just need that one frequency point which is 10, which is describing the signal, and maybe one more point which is defining the amplitude. Now, amplitude typically will be 0.5, which is half of this, because you have one component of 10 and one component of negative 10. Suppose we have sum of three sines, three cosines. So, one is 10, 20 and 30. So, here if you do the discrete time Fourier series, you get the three components back. Again, I am plotting it back to the original analog frequency domain. So, most discrete time signals are aperiodic in nature. Even they are like periodic, we will not analyze periodic functions, because the obvious reason is periodic signals vary from negative infinity to positive infinity, and negative infinity is much before we were born, and positive infinity is you do not know when it will end. So, naturally we will restrict in practical signals which are aperiodic in nature of finite length. So, in this case we have our discrete time Fourier transform, which is given by this equation x of n e power minus j omega n, and this gives you the spectra, and naturally since this is aperiodic in nature, you get an continuous spectra. And second thing is that this spectra, as we learnt in the previous video, that this has a range of negative pi to positive pi, something like this. because any other frequencies will be folded back in this region because of aliasing. So, this is one example. So, here I have a signal, this is some random values which I have selected to show you. So, this signal is changing from some negative values to positive values in the time domain, and this is typically the DTFT. So, if you see the 0 frequency, it is not exactly 0, there is some small value which is the average or the sum of these components. So, and again as I said that spectra is not just the magnitude spectra, spectra is a complex valued vector. So, you have a magnitude spectrum and you also have a phase spectrum. Now, like the forward DTFT, we also have the inverse DTFT. So, this inverse DTFT is to recover the signal in discrete time domain from the continuous spectra x of omega by this formula. And here since omega is continuous in nature, we do an integration to get the IDFT. Remember this, that in the forward transform, since xn is discrete, we do the summation, in the inverse we do the integration. And then again x omega is periodic. As I said that here we are just considering the fundamental period from negative pi to pi, but this will be basically repeating itself. Now, the next question is, for all signals do we get the DTFT? So, if the signals are not converging, or in other words if they are not absolutely summable, so it is difficult to get the DTFT. So, for signals that are absolutely summable, that is where the DTFT will converge, we can get the signals spectra. Okay. So, let us understand some properties of the discrete time Fourier transform. So, the first property is linearity. So, the question is DTFT linear? Yes, it is a linear operation and we can prove it very easily using the superposition theorem. Like if x1 n gives capital X1 omega and small x2 n gives capital X2 omega, then a linear combination like a1 x1 plus a2 x2, and if I do the DTFT of this linear combination, we can easily see that it will be a1 the DTFT of small x1 which is capital X1 omega plus a2 and capital X2 omega, and here a1 and a2 are any constant. What about time shifting? So, suppose I have a signal in the discrete time domain and I shifted by some value k samples. So, this is equivalent to multiplying this term e power minus j omega k with the original spectra of x of k. So, this is the meaning of shifting a signal in time will result in multiplying its DTFT by a complex exponential factor. And what this factor is doing, it is not changing its amplitude because it has a unit amplitude. So, it will only change the phase spectra, and this is why phase spectra is also very important in many signal processing applications. What about frequency shifting? What is frequency shifting? So, here we get a change in the spectra in the frequency domain, and this happens when we multiply a complex exponential in the time domain. The next is scaling. Now, this is slightly different from the continuous domain, like I also explained this in time scaling, that this is not just time scaling, but this is also changing the sampling rate. So, this we will or we might also encounter in multi-rate signal processing, where so here this is if a is a value which is greater than 1, that means we are doing a downsampling operation. We are picking say every alternate samples or every samples after say skipping some samples. So, this is something called a downsampler. So, this downsampling will create a spectra which is related to the original spectra by this equation, that 1 by mod of a x of omega divided by a. And then the very common property which is a convolution property, where if you convolve two signals and take their spectra, it is equivalent to multiplying their individual spectra in the frequency domain. And what about multiplication in time domain? So, if you multiply two signals in the time domain, it is convolution in the frequency domain. And then another fundamental theorem which is coming from the concept of energy conservation, which is the energy in the time domain and in the frequency domain will be same. So, how do you find the energy in the time domain of a signal? So, this is you take the magnitude and square the signal values and then sum over n. So, this is your energy in the time domain, and this will be same as the energy in the frequency domain, which is obtained by this formula 1 by 2 pi integration minus pi to pi, because this is the content of, this is the span of your frequency spectra. And again this is basically from minus pi to pi, and the second thing is this omega, as I said, is a continuous variable. So, you get this integration. So, next is symmetry property, which is also very important, specifically when you will learn about the FFT algorithms. So, if you have a real valued signal, so the property says that the DTFT x of omega will have this conjugate symmetry, which means x of minus omega will be the complex conjugate of this. And further, if your signal is real and even, then your spectra will also be real and even. Similarly, if your signal is real and odd function like this, then your spectra will be completely imaginary and odd. And good examples are your sines and cosines, which are odd and even respectively. And these are harnessed to compute the discrete cosine transform and the discrete sine transforms. And now let us try to compute the DTFT of some standard functions, and we start with the delta function. So, if you write the formula, which is this, you see that this will sum to 1, which is very much similar to the continuous domain. Now, how do we get this? So, if you clearly see, so you keep putting the values. So, here only for n equals to 0, your delta function will be defined to be 1, and this is also 1. So, 1 into 1 is 1. So, this is the plot, and you must be wondering that why I have not put these edges at negative pi and pi, because there will not be edges, and if, as I said, that this DTFT is periodic and it varies up to infinity. So, this is just the fundamental period when you have the values defined to be 1 from negative pi to positive pi. Then what about a sinusoidal signal? Now, I already said that sinusoidal signal like a cos wave is periodic and it will be extending from negative infinity to positive infinity. So, you typically would like to perform the DTFS, the Fourier series, but even if you perform the Fourier transform, by putting it in the formula, you will possibly not be able to come to this value because of the absolute summable problem, because this cosine and sine are not absolute summable when considered from negative infinity to positive infinity. So, what to do in this case? So, there is a special way by which you can find, but from the concept you already know that sines and cosines will have two frequencies at negative omega naught and positive omega naught. And if it is a single complex exponential at omega naught, this will have only one frequency component omega naught. So, this is a pure wave where there is only one frequency component, and this again comes from the property of shifting, frequency shifting. So, the next kind of transform is your discrete Fourier transform. So, as I said, this omega axis is continuous from negative pi to pi. How do you write an algorithm to implement this, or how did I implement this? So, typically I have to use some samples of the omega, say I take some 1000 samples of the omega from minus pi to pi, and then I can plot based on the function. but really when you want to put it on a digital hardware, because digital signal processing is mainly computing on digital signal processors or microcontrollers. So, you need some specific points. So, that means the spectra DTFT needs to be sampled. So, if I sample the spectra using n number of points, this is nothing but this is called my n point DFT, discrete Fourier transform, and this solves the practical implementation problem of the DTFT, or in other words I represent this DTFT by n points. So, this is again solving this leakage problem. See, like when I have a windowed sample, so my two frequency components, say these are the two frequency components of say minus 0.5 and plus 0.5. These are appearing at two peaks, but there is a spread and there are all side lobes. But if I take just two samples, although these are not exactly zeros, so these are, I have done some kind of post processing to make them 0, but these two prominent peaks are now very easily visible in what is called my n point DFT. So, this is frequency domain sampling, I am sampling the frequency spectra. So, how do I define my discrete Fourier transform? So, this is a discrete version of my DTFT where I take n samples, as I said. So, this 2 pi region is divided by n points, and what is the spacing between two consecutive points? It is 2 pi by n, and this is the formula for my n point DFT. So, let us find some properties of this DFT. The first property is periodicity, which is very important, like my DTFT, that so DTFT was periodic with a period of 2 pi. Here my DFT is periodic with a period of n, which means that my signal sample x of n, which has value 0 to n minus 1, its DFT will be periodic with n. And also now when we see a periodic discrete spectra or line spectra, this means in the time domain also my signal should be periodic. So, how this ambiguity should be resolved? So, it is assumed that in the time domain also that xn, which is a finite duration, has a periodic repetition. So, that signal is repeated infinitely to make it periodic, or you do a spectral analysis of the periodic repetition of my xn, and then you get this line spectra, which is my x of k, which is my DFT. And linearity is just like your DTFT, so I am not explaining it again. Now, symmetry also is very important here, but what is important to look at is that it is conjugate symmetric for this. So, x of n minus k will be x conjugate k. So, for a real valued signal x of n, the DFT coefficient x of k will exhibit conjugate symmetry, and this is very important specifically for the development of my FFT algorithms. And these properties are very much similar to the DTFT. So, I will just quickly go through them, like when I have a shift in the time domain n naught, it is multiplied with this phase factor. So, here you see that this omega is typically replaced by 2 pi k by n, and rest is kind of same. So, next is frequency shifting, and here the main thing you have to understand is that since both this x, which is the DFT, and the small x, which is the time, they are considered to be periodic extensions. So, we have this formula modulo. So, here this is not just a linear shift, but it is a modulo n shift. Modulo n shift means, say if the signal is periodic like this, so after this I get this value, which is same as the first value. So, this is like a circular shift. So, the shifting is happening in a circular manner. Same with convolution. So, here if you see that if I, so in your DTFT, so your spectra multiplication is equivalent to convolution, which is linear convolution, but in your DFT it is the circular convolution, which is denoted by this symbol. So, what is circular convolution? So, in linear convolution you have this signal and the kernel and you keep on shifting this. So, in circular you basically have circular kernels and you keep on shifting this, shift multiply, but perform circular shifts. And you will also come to know in the hardware there are circular register or barrel shift registers used for this purpose. Then multiplication is in time will give convolution in frequency, but again this is circular convolution. And then Parseval's theorem, which is just the energy conservation, which is given by this relation, and circular time reversal, that here if I do not get just x of minus n, rather I say it is n minus n, which means it is reversal with respect to time or with respect to the periodicity, because this signal is periodic in nature, something like this. So, if you see this is like a circle rotating. So, the circular rotation or circular time reversal, I would say, will give DFT, which is the conjugate of the original DFT. Like if x of n gives me x of k, then if I do a circular time reversal, then it will be the complex conjugate of this. So, what is this circular convolution? Why so much hype about this? So, this is a type of convolution which is applied to periodic sequences, like as I said that there is a circle which is rotating. So, there are some conditions, like say you want to convolve x of n and h of n, and both can be of different lengths, but in circular convolution both should be of same length, because you are doing things circularly. So, say if there are 4 values of the signal, so one signal you keep fixed, the other signal you rotate and then multiply, add, rotate, multiply, add, rotate, multiply, add, like this. So, this is given by this formula. This modulo operation is just depicting the same, and this is because say if you have a signal 1, 2, 3, 4. So, since this is a periodic extension, so after 4 1 will come and before 1 4 will come, like this, like this. So, you take any window, so when you are shifting, see it is like a circular rotation. So, let us take an example to make this clear. So, we have 2 sequences, both are of length 4. This is very important, that both have to be of the same length. So, this is the definition which I said, and now using the formula you can easily calculate, and I will not waste time on this, and you can verify this is the result. And there is one more matrix multiplication method which we can discuss quickly. So, you have 2 matrices. So, this is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 and 1, 2, 3, 4, and this is probably 4, 3, 2, 1, 4, 3, 2, 1. And if you calculate this, you try calculating, you will get this same result. So, this is one easier way to do the calculation by hand. Let us try out quickly. So, 4 plus 1 into 4 is 4, plus 4 into 3 is 12, plus 3 into 3 is 9, plus 2 into, sorry, did I do mistake, 3 into 2 is 6, and 2 into 1 is 2. So, if I do this, this is 10 and this is 14, so 24, this is 24, this is matched. Second is 2 into 4 is 8, 1 into 3 is 3, 4 into 2 is 8 and 3 into 1 is 3. And if I do, so this is 6 and this is how much, 6 plus 16 is 22. 22, and if you check, this is the result. So, thank you very much. We will meet again. Hope you enjoyed this lecture. Have a nice day.